Welcome to tonight's lecture on engineering limbs, helping amputees walk in Vietnam, which will be presented by Professor Peter Lee. And my name is Ivan Mariels, I'm the Dean of Engineering, and it's really a pleasure to welcome all of you here tonight to listen to what I also think will be a very exciting talk. But let me start with acknowledging the traditional owners of the country on which this event is taking place, the Wurundjeri people, and we pay our respects to their elders, past and present. We'll hearing from Professor Peter Lee. Peter is professor in mechanical engineering at University of Melbourne, and he will talk about basically what is dear to his heart, I would say, his passion in life, biomechanical engineering, and in particular going to talk about low-cost artificial limbs. And I won't steal his thunder, although there's a lot more here about the talk. But Peter is a specialist in biomechanics, actually cellular mechanics, I think the way they call it nowadays. He got his PhD degree from University of Strathclyde, and he also had some postdoctoral studies there. And he came to us via Singapore, which I think maybe his native place actually. And he worked there at the Materials Research and Engineering Institute in Singapore, the Defense Medical Environmental Research Institute, and the DSO, the Defense Science Organization, national laboratories, all in Singapore, as well as the National University of Singapore before arriving here. So really, it's a real pleasure to have Peter here tonight, and I'm looking forward to the talk, Peter. Please welcome Peter.
Can you hear me quite well? All right. Thank you so much for coming here tonight. I know you spend your precious time to join us here, and thank you even for the very nice introduction. Right. So today I'll be discussing about some of the work that we've done in Vietnam, primarily looking at lower limb amputees. Right. So I think from this slide you can very quickly tell that this person hasn't got his right leg. So this is a typical what we call a below knee amputee. Sometimes the more technical name will be transtibia, a transtibia amputee, where the amputation is at the below the knee where the tibia is, bone is. So you can see that he's also a smoker, right? Yeah, but I can tell he didn't lose his leg because of smoking. So if you smoke, you can. Right, so he actually lost his leg due to the landmine, fortunately. Now I'd like to show you a video of him, when we first met him. This is him. You can see he's got a really a slow and pretty cool gait, right? He just takes his time. It was quite difficult getting him to do a biomechanical test because we say, hey, walk. And we want to measure his walking speed, capture all the parameters. But that's how he walks, right? He just takes his time. Right? So maybe, some of these biomechanical parameters are important to us, but in this case, we can clearly see comfort and probably coolness, probably, rate better in terms of how good the leg is actually functioning. Now, the main reason why I'm showing you this video is really to show you his ability, right? Because when we talk about disability, clearly, this person is able. I know he's going to walk out from this clinic, and then he's going to go about his own work, right? And he will contribute to the society, right? So bear in mind, all he had here that is different from us, or from most of us, is that he has a prosthetic leg, all right? Now, so I'm going to spend the next, maybe 30 minutes or so talking about our story, right? So our story, of course, has to do with Vietnam. This is a very nice picture that I took in Ha Long Bay, and I was on a sort of a boat with a Vietnamese flag. Can't hold myself, and so I'm a bit of a photographer as well. Now, so, but I like to. This is a selfie, okay. So I like to, first of all, before even I start, to acknowledge the team. because without this team, we wouldn't be where we are today. So Jim, you'll find him there because he's the only bearded guy, right? Now he's a rock star. Now he's a rock star prosthetist in Caulfield Hospital, senior prosthetist. But he's actually play lots of music and he's in the band, so he's truly a rock star. And he's quite a unique person with good special skills. He works in developing countries for quite many years. And then when he saw this project, in fact, Mark Groff is here. He used to manage. He's the manager of Jim, and he recommended, "Oh, Jim, you should get onto this project." And he jumps onto it. And since then, he's been a fantastic contributor, our main key clinical person. And then Noah, right, is here. Right, Noah is a sports exercise scientist. So he's been the key person helping us to collect all the biomechanical data. Sheridan, you're here, right? Sheridan, she's a PhD student, so she's really the one that gets all of us organized. She makes sure that we do our job right. And there's also Ricardo there. Ricardo is only there because he wanted to go to a holiday in Vietnam. So he sort of used us as, so I'm kidding. He's a master's student. So we have many students like Ricardo who has joined us in our trials. I think over the couple of years, about 10 students actually come on board and contributed. And that lady here is probably the most important person. She's the reason why we are doing this. And she's really the one that sort of put a smile to our face. You can actually see a bit of a smile behind that beard in Jean, right? I'm sure you can. Now, also, I'd like to acknowledge our funders, right? Without our funders, we wouldn't even be doing this work at all. So, PCAST Foundation for Victoria funded our project, Rotary Club Richmond, and also Promobility Foundation from Sweden, right? Now, so what you see here is really the prosthetic leg. On your left, on your left, it's a sort of a transtibial prosthesis where the amputation is below the knee, and if it consists of the socket, the shank, and the foot, and the components that puts them sort of hold them together. Now the other leg there you see is really what we call a transfemoral prosthesis. And the only difference between the two, besides the shape of the socket, is also there's a knee joint there. Now, so to this presentation, I will be focusing primarily on the transtibial prosthesis. Now, so if you look at the prosthesis, you got the shank, the foot. They are fairly standard components. They're almost like off the shelf. You can buy them and put them together. The only component, right, which in my opinion is the most important one, is when the man actually interfaces with the machine, is the socket, right? Now, you can see in the socket is really different because it's supposed to be different one from the other because all of us are shaped differently. So the socket is shaped uniquely, to the shape of the amputee. Now, so in this case, this is, it's all the socket shapes in one of our trials. And we put them together, take a picture, you can see immediately, oh, they're big sockets, they're small sockets, and they're shaped quite differently. All right? Now, so the reason why I emphasize this is that you really need a trained person to build this socket. Now, so how do you go about making this socket? So to prosthetists, this is a standard process, right? First of all, you get the amputee, and then you do all the necessary measurements. You take measurements just using measure tapes. All right, you record all these numbers because you need to reference that later. And then you take a plaster wrap, stuff that if you fracture leg, or arm, you got to plaster wrap it. So you plaster wrap the residual limb, which is the amputee's limb. And then you take that wrap out, okay, and you make a positive mold, right? Now, once you got the positive mold, you then compare the size and the shape of the positive mold with some of the measurements that you have taken. And then from which you do probably the most important step in making the socket, which is the rectification process. Now, this is when the prosthetist starts to, shave off the plaster, all right? So you can imagine when you take plaster off, it actually, produces more pressure, right, when you make the socket. And then if you slap plaster on, you increase the volume, you actually create relief, right? So this is where, you know, a lot of skills is then poured into making this socket. It's actually when the prosthetist starts to use his experience, his training, and start to shape it. And after which it's shaped, then you laminate it, right? You can actually drape plastic over it, and then following them, you can, you know, make your socket. Now, so I want to, you know, take you to this point so you understand the socket. Okay, that component is where we're going to be focusing on. Now, so what is the problem, okay, in developing countries? Now, the problem we all know is huge number of amputees. So in Vietnam alone, this is a statistics that, you know, I use quite normally. I should really update myself. This is 1996, but it's very difficult to find good stats. But even then, we're talking about 200,000 amputees, and increasing, you know, 3 to 4% per year. I mean, some article today are saying maybe 400,000 amputees. Now, so a lot of the early days, amputees, you know, the loss of limb is due to landmines, due to conflict. But today, right, it is quite different actually. Today, a lot of amputation are due to, you know, this is me in a cab taking a taxi, and I saw this. So you can see, you know, transportation, people are moving, a lot of risk accidents. So these are becoming the key reason of limb loss, right? So today's environment is quite different. And, you know, 20, 30 years down the road, you know, Vietnam will be same as us, right? Most of our limb loss will be due to, you know, diabetes and vascular diseases, right? Now, so moving on, with regards to the problem with developing countries, this is a report by the World Health Organization in 2004. Now here you see that, you know, if you take Asia, Africa, South America, or Latin America, right, we're talking about 25 million people needs prosthesis and orthosis, right? Now, and we all know, as I showed you in the very first video, you know, once they have the appropriate device, they can function, you know, very well in society. Now, but what is very interesting is that in 2004, this report was primarily done to highlight that, you know, there's only 24 schools in developing countries, all right? And in these 24 schools, 400 personnel are trained per year, okay? Now, so we're talking about 75% of developing countries have no prosthetics, orthotics training at all. So where are you going to get the prosthetists to, you know, make the prostheses? Right, and sometimes we take for granted, right? But if you think about it, it's so true when you say mobility, right? It's really the first step to our basic rights. Again, if you allow a person to be able to move, you know, make a living, I think this is something that, to a certain extent, is our responsibility. Now, moving on, back to our story, how you all started. Right, how, you know, we got involved in Vietnam. Now, so most of you would have seen a picture like this, right? Right. So you see, you know, amputees running in the Olympic race. So very soon, you know, one day we may see an amputee, you know, winning the Olympic gold medal, not the Paralympic gold medal, right? So that is a possibility, and that's a likelihood. Now, so a prosthesis like this, very high-tech, lightweight materials, you know, energy storage, it could do a lot, and it's very common in places like, you know, our country. Right, but the reality is this, in developing country, okay, now the artificial limb that you see there is going to look something like this, okay? Now, so this is what we call the International Committee of the Red Cross prosthesis, the ICRC polypropylene technology. It's amazing, it's all polypropylene except for the rubber foot. And you know, all these plastics, if you make a mistake, you just dump it, melt it, and recycle and use again, right? So it all comes in sheets and, you know, injection molded components. But quite interestingly, ICRC make prosthesis. You know, you always, you can't connect, right? ICRC is a huge organization. Why do they even bother to go, and why can't they just go and buy, you know? But it's quite interesting. A lot of commercial companies are not really into developing countries prosthesis. That one, partly there's no money to be made, but so ICRC actually developed this over the years, you know, and currently is used all over in developing countries. Now, so this is what we have today. Now, interestingly, when we got engaged with ICRC, you know, in developing countries, we were really looking at the durability of this prosthesis, right? So, you know, we see patients coming into clinics like this. Now, so you can clearly see there used to be a foot here, right? And, you know, today it's all gone and disappeared. Now, why didn't this person get it fixed the moment it breaks? Because, you know, they live in rural areas, they don't get access to clinics, and, you know, and without the leg, right, they can't work. So they just keep going. I mean, this leg goes into, the other one, you can clearly see this rubber. So it's gone into paddy fields, gone into, you know, extreme humidity. Right. So when we got involved, we basically did a whole lot of tests. We took the leg, you know, we conducted what we call the ISO standard test. Now, so the International Standard Organization test is primarily for prosthesis to go through the test such that it can get marketed. Of course, ICRC didn't build this for the purpose of marketing. It's really a need, right? Nonetheless, we got involved with them. We've been doing all these tests. We even got involved in working on some of the designs. So you can see, you know, the knee is a fairly standard uniaxial type knee. And then what we did was we developed a wedge lock to, you know, give it more stability, right? And you know, fast tracking prosthetic feet, that's another project. And all this project, amazingly, is just done by, you know, undergraduate or master students, right? So if you're one of them, you know, there is hope. All right. Now, so we got involved with, you know, but interestingly, we also did quite a bit of socket work during the early days, right? Now, I'm going to share with you this for a purpose. So as engineers, you know, we are also tempted with high technology, you know, advanced technology. So at that time, you know, CAD/CAM, you know, computer-aided design and computer-aided manufacturing is really the in thing. And why not? Why not, you know, borrow this technology and use it for prosthetics? So here you see that, you know, an amputee putting the residual limb in a laser scanner. It got scanned. And then you produce a digital image, and the process then modified the digital image, and then send it to a milling machine, carve it out, and then, you know, you make the socket. So if you compare the CAD/CAM process, what it really did was it sort of replaces this bit, right? So you only carve out the plastic, and then from there, this will be a sort of a rectified cast, and then it goes on and you can make the socket. Now, when we got involved in projects like this at that time, this is quite many years ago, maybe more than 10 years now, we look at the whole process and then we say, hey, we can, you know, engineer again, we can make it even better. So we started playing around with what we call a direct or rapid socket manufacturing technique. So instead of, you know, the milling machine, we start to design a 3D printer. Okay, now, of course, all of you say that, oh, 3D printer, you know, I've got one sitting at home. But, you know, wind back, you know, 10, 15 years ago, yeah, they're really expensive. Okay, so we actually built one, all right? Okay, a big 3D printer, we built one, and then, you know, layer by layer technique, we make a nice socket, and from which we even tested in ISO. It passed all the tests, we put it on patient, and it works fine. Now, we even went one step further. We start to say, oh, you know, we can make this whole process even smarter. And here we are, we introduce what we call finite element technique, allows to predict pressure, right? And then you can actually predict the pressure map of the prosthesis even before it's made, right? So it gives real-time feedback to the process. So we were working with a company at that time, and then, you know, you can then make the socket. But interestingly, right, I share all this with you because if you look at CAD/CAM today, it was a big deal. You know, there's a lot of talk about it. We were even talking about, you know, central fabrication. You know, with a setup like this sitting in, say, in Vietnam, and then sending out prosthesis to Cambodia, Laos, and Myanmar. But today, you can hardly find, a proper working system. A lot of them are in clinics, but they're used for visitors. Okay, right? So what happened there? What really happened there? Now, in my personal opinion, I think it is this. It is this bit, right? The prosthetist is still involved in this whole process, right? The prosthetist is involved in this whole process. Essentially, the CAD-CAM is really a reproduction technique. I mean, to be fair, there are still systems that are put into good use, and it's highly efficient. But try bringing this to a developing country. It's hard enough to train a prosthetist. It's even harder to train a prosthetist to become an engineer, right? So there are these concerns. I think using appropriate technology is really a key point that I like to drive. Now here again, so with whole business of socket work, we started to then say, can we develop a casting technique that actually reduces the skill dependency? And then, whether we can create a socket that reduces the fitting errors, time, and cost. Now, before I go into this aim, right, I'd like to show you, these are the typical, amputee stump or residual limb. You got a very short limb, right, and you can even see that in this case, this particular patient, when he came in, you start to see their calluses, they're forming in places that, are likely to be taking a lot of load. So essentially, this person wasn't given a good fitting socket. Now, you also get very long limb like this one, right, where it's very bony. So a challenge is actually to find a technique that is able to fit, this wide range of residual limb. Now, so where sort of a bit about history of development of transtibial socket. Now, so in the 40s, right, when we look at prosthesis, it's really just a plug fit, a very sort of loose plug fit, and then you've got a corset that holds up the prosthesis. Now, then in the 50s, after the war, that's when, a lot of biomechanics got interested or excited about, making a good prosthesis, right? This is where, a lot of quantitative knowledge comes in and a lot of funding from, the Veterans Association in the US. Now, at that time, what is then developed is what we call today the patella tendon bearing socket. Now, if you all, just start to push a bit just below your kneecap, you find that there's a very tough tendon, right? Okay, in fact, you could push it quite hard and you don't actually feel painful, all right? So at that time, that was sort of pitched as a place where you can actually put load. So in other words, a lot of the load goes there, and then when you stand, you transfer your body weight down the patella tendon and then to the socket, through the socket and then to the prosthesis. There are different variations, of the patella tendon or PTB socket, and then you got, different ways of suspending or holding up the socket. Now, so if you then say, so the anticipated pressure profile of the patella tendon prosthesis or the PTB was something like this. At heel strike, right, you get very high loading, right, at the patella tendon. So you get, on that side, very high loading, okay? And then it sort of, do a reverser, right? And then when you start to do a toe off, right, you're not loading the patella tendon anymore, okay? And then you get that pattern. So this pattern has been actually, say, many times taught in textbook. Oh, yeah, it looks like this. Now, so, but even then, in the early 60s, people are starting to say that, hey, is this going to happen? So this is when, the patella tendon starts to tension, right? The PTB bar that is in the patella tendon bearing socket gets pushed out, right? And once it's being pushed out, you can tell that it's not supporting the body weight anymore. So a lot of research then goes into, is the patella tendon bar in the socket actually doing this work? Now, so how does the patella tendon bar looks like? Something like that. So you can see a bar there, right? And then you look inside, you can see a fairly deep indentation there. Okay? Now, so this has been really the discussion for quite many years. And we started to investigate this ourselves, and we start to rig up, the PTB socket with pressure sensors like this. So you put, lots of pressure sensors, and then you can measure the interface pressure between the the residual limb and the socket. Right? And these sensors are very, very small. They're flush with the wall, so they don't interrupt with the fit. And you can then get pressure profile like this one here. So you get nice pressure profile during walking. So this is a dynamic test. You can see at heel strike, and then it sort of goes down, and then you do your leg swing. Okay? And what is really interesting, okay? This always excites me. Okay? What is really interesting is the pressure profile looks like this. Okay? Now, when you do a heel strike, okay, the anticipated pressure profile we always taught is that you're going to get very high pressure here because the patellar tendon is actually, the bar is taking the load. But we didn't see that. We see a very low pressure there. Okay? And then when you do a toe off, right? Now that is a time where if you start to flex your knee, okay, you find that this tendon becomes really tight, right? And then when it's tight, it actually pushes on the pressure sensor, and you actually get high pressure. But that high pressure is not due to, the bar supporting the load. Okay, now, so we published this, lots of discussion, but it's very interesting. So it got us thinking. In fact, the whole community, I mean, we are not the only group that did this, but there are people who start looking at this, started to say, is the patellar tendon bar actually doing its work? That's where, this whole concept of hydrostatic socket started, okay? Now, so what is hydrostatic socket? So we question about, if you, well, we all know, I think all the mechanical engineers are, expert with pressure cylinders and stuff like that. Now, in this situation, it's hydrostatic, right? Pressure all around are equal. Okay. Now, but with an amputee or a socket, right? You can imagine, right? This is not a closed system. You have the stump inside, and if you apply load, what will happen is tissue will actually flows out, right? Now, when that happens, you don't get a hydrostatic, effect. But I've got a colleague when we were in Strathclyde, he sort of suggested that, hey, maybe we can do what we call a quasi-hydrostatic. In other words, you load before all the fluids actually flow out, you unload it again, because that's how we walk, right? So you may possibly get sort of an even pressure profile, right? And then the whole idea of hydrostatic casting or hydrocast, or today for our system we call it the pressure cast, starts to, give birth, starts to come out. Now, so this is our PCAST tank, an extremely simple tank. Okay. Now you see, this is a typical, mechanical engineering drawing, lots of seals and stuff like that. But what we have is a tank, right? And then in between, we've got a diaphragm and the tank. We just fill it up with water. So the diaphragm is actually a plastic bag. It's quite interesting. When we were looking for a suitable plastic bag, we can't find, some of them break. And then one of our friends got involved. He says, "Hey, I saw this, in aquarium. They sell fish. They got very long plastic bag, and then they fill the top with gas, right? So your fish can be kept alive when you take it home with you. Can we use that? Actually, that works perfectly, right? So." And then the tank. So what I'll do now, I think a video speaks 1,000 words. I'll show you Sheridan. She's here, one of our PhD students. Yeah, a video, right?
So when the patient presents, obviously we explain to them the purposes of the trial. We then wrap their residual limb in a plaster wrap, which they then place into the PCAST tank. We turn the taps and water rushes in, and this water pressure actually moulds the plaster cast to the exact anatomy of the participant's residual limb, so there's no modifications or adjustments required by the prosthetist.
It's okay.
The water pressure also allows them to form the cast in a load-bearing manner, which is similar to when they're standing or walking. Using this negative cast, we create a positive mould. And using that, we can drape polypropylene, a really rugged and durable plastic, around the mould. And this forms the socket. It takes a bit of heating in the oven and it's done, essentially. This is then attached to standard ICRC Red Cross components, which they can use to adjust to the right height for the patient, and they align it so they walk properly and in a manner that's comfortable and efficient for them. And then it's done. They place a cover over the top and they're out the door with hopefully a really functional and limb that they're satisfied with.
Right, so that sort of explained quite clearly. And so if you look at the two sockets, like, so this is a PCAST socket, and then this is a PTB socket. Now, if you look at the cast, right, you can clearly see that in this case, there's a PTB bar that is, typically marked by having the prosthesis, doing indentation at the PTB area, and here is a PCAST socket. Right, then of course, the first thing we do is let's measure the pressure and see what's the difference. And this even get me more excited because, when you actually measure the pressure, right, when you look at the two systems, so the PCAST, this is for the same patient, right, the PCAST and the PTB. You find that at heel strike, the PTB didn't show up high pressure at the top. It's exactly the same as the PCAST, right? And then with the heel strike, even though there's no PTB bar, you see high pressure. So in other words, what's happening is really that there's no difference in terms of socket philosophy between the PTB socket and the PCAST socket, right? Of course, there's many questions. Then where is the load going? How is the load being taken up? And you also clearly see that it is not hydrostatic, right? Because they are high pressure sports. But you can also see that the pressure are a little bit more even, right? Does that increase comfort? Now, so in summary, right, these are some of the observations we made. No reversal of pressure between the PCAST and PTB socket. More evenly, pressure profile can be seen in the PCAST. Hydrostatic is never going to be possible in a system like this. Now, the biomechanical principles, I think, are quite similar, all right? And then the PCAST was able to provide a consistent or comfortable fit. Now, then, with all this information, our preliminary studies published about 3 papers, and then we say, when I moved over to Melbourne at that time, Noah and I decided, hey, it's really interesting, we should really investigate more. And then we approached CAST Foundation with a proposal to investigate the biomechanics of PCAST socket. So the title is something like that. It's not about, let's implement it in a developing country. So very fortunately, we were funded, and CAST gave us money to do a trial locally in Australia for 10 subjects to further understand, to do more pressure measurements. And so I like to tell this story because it's really interesting. So what happened was over the trial, things didn't work out too well. We got delayed. We couldn't get volunteer subjects, and we had to go and face the CAST director one day. I remember this, and Noah and I were all prepared with excuses, right? to say, why we weren't able to delay provide. So we went all prepared, in this meeting, facing, I think there were 3 of you there, the CAST director, and as we were trying to give our excuse, one of the directors says to us, why don't you do this in a developing country? That's where it really matters. Why are you doing this here? And actually, quite interestingly, Noah and I were totally unprepared. We were like, okay, that sounds interesting. And bearing in mind, I've already worked quite a lot of developing countries at that time. So it just struck me by surprise. And of course, at that time, we says, okay, we will think about it. And quite nicely, that CAST got us involved with Rotary. And Rotary was very keen on overseas mission. And we got another grant to just do the trial in Vietnam. And that's how the whole Vietnam project started. So I must say that 30 seconds, encounter I have with the CAST director was probably one of the most important times in my life. As I said, my wedding vows, right? Okay. so you can guess my wife is somewhere here, right? Now, so Rotary got involved, CAST funded project, and what was the project about? So the project was really to implement the PCAST in developing countries. So it's really field testing. So why it is important, because the setting is totally different. We have technicians, not category 1 or a graduate prosthetist working with us. And the first trial was 50 subjects over 2 years. So the main aim was really transfer our knowledge in PCAST to the group in a way to seek the collaboration, but to also convince them that this is something worth thinking about. So the trial looks something like this. We recruit subjects, and then we do all the biomechanical measurements on the original leg, right? And then we fit it with PCAST, and then we send them away. We do initial measurements, send them away for 2 months, and then we do another measurement, and then we send them away for 4 months, and we do another set of measurements. So in the whole process, we're able to track the longer term outcome. We do biomechanical measurements, we do patient survey, we even do the prosthetist or the technician survey as well of how they find using the PCAST. So that work's been published. I can show you a short video of some of the. So this mat is sort of pressure sensitive. You can actually capture walking speed, cadence, like how many steps per minute, and so forth. Well, the pressure cast is here. So we've got people walking up and down, right? This guy walks really well. He's in fact an athlete. I think he's a Paralympic guy representing Vietnam. So in badminton, yeah. So this is how we do. And quite interestingly, we managed the trial quite well. We go there for about a week or 2, and we just continuously churning out sockets and doing the measurements. Now this is a typical set of data. I'm just going to show you one because I don't think you're here for technical presentation. Right, so here's gait speed. Right, gait speed is how fast a person walk. And then this is the original socket. Whatever sockets they come, they take to us. The PCAST, the day we fitted him, and then the pulse. You can see there's clearly an improvement during that period. Now, then, just quite recently, we started to think a bit more about the PCAST. I think we are at a stage where we have proved the concept. We are at a stage where we feel that there's a lot of potential for implementation. Right now, we spoke to a few NGOs, HI, ICRC, and one of the interesting issues has been, of course, cost is one issue. In providing prosthesis. Now, governance or clinical governance, how do you benchmark the quality of your prosthesis that are being produced? And of course, education. Now, these 3 components are fairly critical to a successful process of producing orthopedic devices like artificial limb. So in the Promobilia Foundation proposal, what we did was we set out 2 tasks. One is how to develop a robust PCAST protocol for use in developing countries. And then the second task is how the PCAST protocol will impact clinical governance and technical education. So the technical education bit is something that we are quite passionate about, because we think that we can use the PCAST to help better the skills of prosthesis, prosthetists as well. Right. We were in Vietcong, there were a bunch of students there, and we had a very good, engagement with them. Now, so what is the next step? Right. So, with this, we did this trial. Well, I won't say it's a trial. It's really an education process. Within a week, we fitted 20 subjects. We collected very good data. We have a very experienced prosthetist, Jim, making a PTB socket, and then we compare, or I say compete, with the PCAST, right? So they were looking really good. We are getting the PCAST is successful with almost 70-80% of the subjects, right? But the challenge is then we asked them, which one do you want to take home? Because we didn't allow them to take home 2, Of course, it's about 50-50. I must say we're pretty glad with it. So both legs fitted, they paid PCAST, and 50% of them actually took the PCAST home, right? So this is really encouraging for us. Now, so what's the next step? Right, the next step I think is really education. Right, so we are very keen to move the PCAST and our knowledge of socket biomechanics into a lot of developing countries. We've spent a lot of time in Vietnam. Our partners there know us really well. They know exactly what we are capable of, and now they are using the PCAST for their own purpose. We're basically hands off now. So we're very keen to go forward to Cambodia, Laos, Myanmar, or some of the Southeast Asia region where there's high number of amputees. Now, in research front, you can see that we've only been talking about transtibial prosthesis. What about transfemoral? Another whole set of interesting challenge. So can we do a PCAST for transfemoral prosthesis? And then direct socket. Now, direct socket is really exciting. Here is something that we did many years ago, but you can see here is me putting fiberglass impregnated with resin directly onto a patient's stump, all right? Okay, and then put it in the PCAST, take that, and that is the final shape of the socket. Now that's the beauty with the PCAST, because whatever you cast, that's the socket. And then fit that into, here is a fairly, developed country prosthesis here. This was trial quite some time ago. So material research is the other one that we are very keen with. And of course, how do you sustain this effort? Right, this always keep me awake at night. Affordability, right, whether something like this can be commercialized, right, I don't know. Whether we should even think about open source, right? So if you have ideas, please throw them to me. Now, so I'm going to wrap up my presentation, almost last slide. Now, this is just a railway right in front of Viet Cong where we were doing the trial. So you can see there are people walking there. So every day we walk past it, and we always tell, this railway is not actually used, right? But no, you see big trains coming, right? And so here's the story of one of our very strong I'll just let her tell the story.
Cô đang đi làm thì đến giờ giải lao, cô về cô cho em bé bú. Nên đến lúc quay ra thì có một đoàn tàu đi vào ga. Nhưng mà cô cũng không để ý, hoặc là lúc đấy mình nó như là kiểu mộng du ấy, không biết gì ạ. Còi tàu không biết, tiếng động không biết, nên là nó kéo đi. Nó hút vào đấy, vì tàu đi rất là mạnh. Nó hút vào đấy, thế là kéo đi một đoạn mấy chục mét ấy, là cô bị gãy dập, nó dập lát. Thế là dân ở đó gần đấy đã, hàng xóm người ta đưa cô vào bệnh viện Việt Đức, và sau đó là cái dập lát đấy là không thể khắc phục được, nên là bác sĩ phải cắt, và cô bị tai nạn từ đó.
Và ngoài ra là mọi người biết là người dân Việt Nam sống ở một cái đất nước rất là dài, chiều dài rất là rộng và dài. Do vậy cái chuyện di chuyển đi lại tiếp cận đến dịch vụ dụng cụ chỉnh hình là rất là khó khăn. Vậy cái dụng cụ chỉnh hình phải cần có độ bền cao nhưng mà lại giá thành rẻ để đáp ứng được cái nhu cầu của người dân. Nhưng cái ưu điểm nhất của cái PCAST này chính là về cái thời gian. Nếu mà một bệnh nhân bình thường để cung cấp một cái chân giả bằng công nghệ PP thì phải mất đến 3 ngày, 2 đến 3 ngày. Nhưng riêng PCAST này thì có thể thực hiện trong vòng 1 ngày.
Sau khi cô có cái chân giả này, cô đi bộ, đi thể dục, và cô đi du lịch, cô đi leo núi, tất cả mọi thứ là cô không thấy ngại ngần gì cả. Thậm chí cô leo được lên tận chùa Đồng, thì các bạn thấy là rất là tuyệt vời.
Right, so I'll just end with this slide, and thank you very much for all your time, and thank you for taking your precious time to come here. Thank you.